In a previous video, you already saw this example. This previous movie was about the control flow of an ABC program. It was dealing with things like functions and loops. Now, in this example, there is also a concept involved where this video focuses on, namely variables. This function foo has a parameter val, and this parameter is basically a local variable. A variable is some memory location that can be used to remember certain values, and this memory location can be changed. It can be overwritten. For example, here in this assignment, we assign a new value to variable val. Now, this video is more about variables, different kind of variables, namely local variables, global variables, and things like the scope of a variable. And you will, by the way, of course, also see new things like for loops, so new language features, so that we, by example, learn more and more about the ABC programming language. In this slight modification, we now have two local variables in function foo. We have variable I, defined here, and again, the parameter val, defined here. Now here, it's more explicit that I is a local variable because it's declared here as a local variable, so you have this keyword local, and it's used here for counting how many times we are executing this loop body of this while loop. Now let's review the control flow of a loop here. So we first have this expression where we initialize I with the value 0, so we can visualize this like that. I gets set to 0. Now variable I remembers the value 0. Until we change it, we can reuse this value. Then the while loop has this condition val is smaller than 10. So this goes into this diamond shape. Then if this condition is true, we execute the loop body, which consists of two statements. So first we have here val gets overwritten with val times 3. So we have this assignment for val, and we have now another assignment for this variable I. So I gets overwritten with I plus 1. And then we go back to check whether the condition is true. So this happens only if the condition was true. If the condition is false, then we continue after the loop. So that means we continue with this print f in this statement. And here we basically just print the value of I. So again here, this placeholder %t gets replaced with the value of I. And then we have the return statement. Okay, no big deal. Try this out. And also try out what happens if you print out the value of I here. So before you set it to 0. So basically you can copy this line here and maybe change the text to something after local I equals. What you see here is an example for undefined behavior. A local variable, if it's not initialized like here, does have an undefined value. So in this example, you probably just see that the value printed out here might be different in the first and second call. It also might be different depending on what kind of optimization levels you use when you translate it into an executable. So here, undefined behavior is just something annoying, but in general, it can be really dangerous. It might mean that sometimes your application, your program crashes, sometimes not. Maybe it's erasing your hard disk or is doing something really bad. The question, of course, will be why does a language like ABC, C, C++ does allow something like undefined behavior? Why doesn't the language protect you from stuff like that? But that's a different story. For now, keep in mind that definition of a local variable like here is a dangerous thing. Just assume that you would later squeeze in some code in between this definition and the assignment of 0 to it. Then this code should not access the value of I. Otherwise, you have undefined behavior added to your code, even if it was correct before. What you usually should see is a pattern where the definition of a local variable also initializes it. like in this example, where we basically do the same thing. The compiler will generate from that the definition of variable I and then assigns a value of 0 to it. And of course, you can use a different value from 0. And then it cannot happen that you squeeze in some code which is accessing a local variable with some uninitialized value. So this is another example with some dangerous code, which should ring all alert bells, because we have here a local variable definition which is not initializing this variable. And you should be aware of that before you even see that we have something new here also, the for loop here. Now let's fix the problem with the uninitialized local variable later. Let's first look at this for loop, and let me show you how you can explain the logic behind this for loop with a flowchart. In the for loop we have this expression here, the init expression, this condition for checking whether the loop body should be executed, and this so-called update expression. And the logic is now the following. First, this init expression, in this case I equals 0, gets executed. And after that, the condition is checked. The condition val less 10. If the condition is true, then first the loop body gets executed, which just has one statement with this assignment. Val gets overwritten with val times 3. But then we not immediately go back to check the condition. After the last statement of the loop body was executed, also this expression here, the update expression, gets executed, which is incrementing I by 1. And after that, we go back to check whether the condition is still true. If the condition is false, then we continue after the for loop. That means with the printf here. Now, how can we fix the problem with this uninitialized local variable? Let me erase my handwriting here. Of course, we simply could also initialize I when we define it. Then we actually no longer need the init expression here. We simply could remove it. An empty init expression is allowed. By the way, also an empty update expression is allowed. You also can move this update expression into the body of the for loop to the end. Then basically, if you look at the flowchart of what is left now, you have the same flowchart as in the previous while loop example. That means with this for loop, we basically express a while loop. Now, the advantage of a for loop and why you sometimes want to use a for loop instead of a while loop is the following. In this for loop, we see in one line the initial value of I, the value of I that you have when you enter the loop body. And you also see in this line how the value of I gets updated after the loop body was executed. And this is sometimes a big advantage because it means your code is more readable. You better understand the logic when you look at the code, and more readable code usually also means less error-prone code. So it's easier to check whether your code is correct. Now, here we still have the problem that I is for some time uninitialized, and if you squeeze in some code between here and here, you have this problem that you saw before. So what you can do is actually define in the for loop the variable I. You see the local keyword is now here. That means we have now a initialized local variable, which is better code. In the same line, we still have the expression for updating the variable. But you also see that I now move this printf statement into the loop body, so that in each iteration we see the value of I. Now, the whole purpose of introducing this local variable I was for counting how many times in total the loop body was executed. So actually we are just interested in the last value of I. So maybe we should move this outside of the for loop, after the for loop. But then if you try that, you get an error message that this variable I is unknown or not defined. The reason for that is that every variable has a scope, and you only can use a variable within its scope. Now the scope of variable I begins here after its definition and ends with this closed curly parenthesis. So basically variable I has this scope. Parameter val, by the way, has a scope beginning from here and its scope ends here. So that's the scope of variable val. Now let's look at an example where it makes a bit more sense to have a local variable where the scope is limited to just a for loop. And here, by the way, function foo is also doing something more useful. It's computing the factorial of its parameter. And the parameter is, by the way, now called n. So it's computing n factorial. So the scope of n is this part. Then we have another local variable. In total, we have 3 local variables. We have also variable result. And the scope of result is this part. And you see it's initialized with 1. We also have another third local variable, I, which is also initialized. And the scope of I is this part here. Now we also can now think about the logic behind that. The result of n factorial should be 1 if n is 0. If n is 0, then check out, the condition would be false. So we would not enter the loop body at all. And otherwise, we always begin with I equals 1. We check that I is smaller or equal to n. Then we enter the loop body. In the loop body, we multiply result with I. And then after the loop body was executed, we increment I. And of course, here you also could do some optimizations. Check out the flowchart and make sure that this makes sense. We also could initialize I with 2. Then the following would happen. If n equals 0 or 1, we would not enter the loop body at all, because if we initialize I with 2, the condition would be false if n equals 1. Now here I applied a different kind of optimization, not an optimization that would somehow speed up the program. It still runs as fast or as slow as before, but an optimization with respect to readability and most of all typing. You see that I saved some space on this slide because I changed this part here and most of all this part here. Now let's begin with the expression for updating result. What you see now is equivalent to what you saw before. This is equivalent to result gets overwritten with result times I. And some similar operator, similar to asterisk equal, you have for addition, subtraction, division, and the modulo operation. So that means for incrementing a variable by 1, like I, we also could simply write I plus equal 1. And this would be equivalent to each other. But this special case for incrementing a variable by 1 is also taken care of by this plus 1. And something similar you have for decrementing a variable by 1, you could write minus I. Let's continue with another more academic example, an example where we have 2 variables with the same name, variable I, defined here and here. But if you compile this, the compiler doesn't complain. And this is interesting because if you would, for example, define here another variable named I, the compiler would actually complain that this variable I was already defined within the same scope. So here is no name conflict because these two variables have different scopes. The scope of variable I defined up here is this scope. And the scope of the variable I defined here is this part. Now, if we, for example, access here variable I, then this refers to the variable in the red scope, so to this variable. If we access variable I here or here, then it's referring to the variable defined here. How this works internally is the following. The compiler simply gives internally these variables different names. So for example, this could be called internally I1 and this here internally I2. Then the compiler would say, okay, this here is I1 for me, this is also I1, and this is how the compiler is basically resolving this name conflicts. So this would be I2. So for the compiler, this variable I is a different variable from this variable. So the compiler doesn't have a problem. But usually we as humans do have a problem with that. And this is called shadowing a previous definition of a variable. So this variable I here shadows this variable. So usually it's a good idea to simply use a different name. Now on the next slide, I'm doing exactly the opposite. I again have this variable I here, not in conflict for the compiler with this variable. And I have a third variable, which is in this case a global variable. Now actually there is a lot to say about local and global variables, but in this video I will just point out a few basics. First, you, for example, could try out what happens if you type in here local instead of global. Then you would get an error message because outside of a function you only can define global variables, not local variables. A variable always has a scope, so also global variables have a scope. The scope ends with the end of the file, so down here. And it begins with its definition. So this is the scope of the global variable I. So within function foo and function main, we could access variable I. And this means if we, for example, print out here the value of I, it's printing out the value of this variable. Then here we assign to this variable the parameter val, and this will become interesting when you call this function foo a second time, because that means the second time you print out the global value of I, it no longer will be 13, but instead 1, because we invoked function foo the first time with 1. Then we have here a local variable within function foo with this scope. That means here and here we access this variable. And then we have a third variable I with this scope. And that means here, here, and here we access this variable. Now, after training our understanding of scopes and figuring out what variable we actually mean when we use it somewhere, let's look at this example where the scopes are easier to understand. We now have two global variables, n and result. The scope is this part here. And in this case, the variables n and result are basically used instead of having return values and parameters in functions. And you will see when you write your own compiler, local variables and also functions with parameters are not very hard, but not the first thing you want to implement. And here basically n and result is used for passing arguments and getting return values from a function. before I invoke here function foo, I simply set the global variable n to 1. Then I call function foo, which is computing the square of n, and it's overwriting the global variable result. And that means afterwards I can access what function foo computed. So basically here n and result is used for communication between function foo and function main. And in the second call, or before the second call of function foo, I first set n to 2, then I'm computing with a call of function foo the square of n, and afterwards I simply get the result by accessing the global variable result. Now, from this example, it might not be clear that global variables in general can be dangerous because it's hard to keep track of things. But assume that after the definition of these global variables, we have lots of functions. Then all these functions could access and modify these global variables. And for you as a programmer, it means that you have a lot of places where you have to make sure that you only access these variables in a correct way. And you have to remember these things. Now, if for some reason you have to use global variables, for example, because you have to use a programming language that doesn't support parameters and local variables, maybe your first own programming language, then you at least can make your life a bit easier by following certain naming conventions. For example, if we would call this variable foo underscore n, then of course we have to change this here and this here and this here and this here also. Then it's kind of clearer that this variable n belongs actually to function foo. And similarly, we could rename this into foo underscore result. Then of course we also have to change it here and here. And then it's somehow clear that these variables only should be used together with function foo. Now, just for fun and not for showing you good programming practice, let's finish with this example where function foo is actually recursively computing the factorial of foo underscore n. And the result is stored in foo underscore result. Here you basically see the conventions for how to use this function. You have to initialize foo underscore n with the argument. You also have to initialize the result variable with 1, and then you can call this function. Now, this is actually interesting because only few language features are used here. Global variables, so we completely avoid the need to talk about local variables in this case, and recursive function calls. Now, when we do some assembly programming, you will see that this is not the first thing that you realize in an assembly program. It requires some understanding about how to deal with global variables. It also requires to understand how a stack is used for function calls, for knowing how a function returns correctly. So with this in mind, that we basically will go here into the details, this still might be an interesting example for the next weeks.